Dear children, now let us discuss about the statement and proof of the two theorems on circles. They are the theorem number 10.1 and theorem number 10.2. What is the statement of the theorem number 10.1? The tangent at any point of a circle is perpendicular to that radius through the point of contact. What is the statement? Write that the tangent at any point of a circle at any point of a circle is perpendicular to the through the point of contact. So what is the statement of the theorem 10.1, which is a theorem on the circle, first theorem on the circle. The tangent at any point of a circle is perpendicular to the radius through the point of contact. So let us draw the circle. So let us draw the figure. Here O is the center of the circle and P is a point on the circle and XY is a tangent. XY is a tangent. Let us join OP. Here O is a center, P is a point on the circle, then OP becomes the radius. Right? We are given a circle with center O. We are given circle with center O. Circle with center O. And XY is a tangent at a point P. XY is a tangent at P. XY is a tangent to the circle tangent to the circle at P. Now what we have to prove? We need to prove that what we have to prove? We need to prove that OP is perpendicular to XY. Say right. We need to prove that this OP is perpendicular to XY. What we have to prove? we have to prove that OP is perpendicular to XY. OP perpendicular to XY. You know that for a given line, you can draw any line. For example, this is a line, and from a given point outside the line, you can draw any number of line. And out of that, the line which is perpendicular is the shortest, and the shortest is the perpendicular. So here we have to prove that OP is the shortest distance of all the lines that can be drawn from O to XY. So let us draw one more line by taking the point Q other than P. So that is the extra construction needed here. So let us take here. Let us take a point Q on XY, or you write take a point Q. Take a point Q other than P. Take a point Q on XY other than P. So you take a point Q on XY other than P and join O and Q. Here you observe the point Q lies outside the circle because XY is a tangent. Only one point lies on the circle, that is P, and Q naturally lies outside the circle. If Q lies on the circle, then XY becomes secant, not tangent. So you write that the point Q must lie outside the circle. The point Q must lie outside the circle. Reason? Because XY is a tangent. XY is a tangent at P. XY is a tangent at P. So P must lie on the circle. As P is the point of contact, Q must lie outside. Therefore you can say that as Q lies outside the circle, it must be greater than OP. So write, therefore OQ is longer than the radius OP. OQ is longer than radius OP. That is what we can write, OQ greater than OP. It happens for every point on the line XY except the point P. This happens for every point on the xy, every point on xy other than P or except P. Here P is a point on the circle and OP is a radius and Q is outside the circle, therefore it is greater than OP. The outside point is joined to center, so the line joining the center and the point outside the circle is always greater than the radius. So then what becomes? OP is shortest among all the lines that can be drawn from O to XY. Therefore you write OP is shortest of all the lines or shortest of all the distance, let us say shortest of all the distances from the point O to XY. From the point O to XY. Therefore you can say that the shortest distance becomes the perpendicular. Therefore you can say, therefore OP is perpendicular to XY because the shortest line becomes the perpendicular. Second theorem on the circle, that theorem is theorem 10.2. And what is the statement of that theorem? The lengths of tangents drawn from an external point to a circle are equal. Let us read the statement. The lengths of tangents drawn from an external point to a circle are equal. Lengths of the tangents drawn from an external point to a circle are equal. This is the statement of the theorem 10.2, which is the second theorem on the circle. Now let us draw the figure to prove this theorem. Draw a circle with center O. Here O is center of the circle, and you take a point outside the circle which is called external point. Let us take P is the external point, and you can draw two tangents from the external point P to the circle. So take them. One is here and the other one is here. These two are the tangents, and the point of contacts are Q and R. Here what you have to prove? We have to prove that the tangents are equal. PQ is equals to PR. That you have to prove. So note down what are given here. We are given a circle with center O. We are given a circle with center O, circle with center O. P is a point lying outside the circle. Here the word external point is there, so you take P is an external point. P is an external point, or P is a point lying outside the circle. PQ and PR are the tangents from P to the circle. PQ and PR are two tangents from the point P to the circle. Two tangents to the circle from P. This much is given. What we have to prove? We have to prove that PQ equals PR. We need to prove that PQ equals PR. So we need to prove that PQ equals PR. So to prove this PQ equals PR, you have to take the congruency of triangle. So we need two triangles. To have two triangles, we have to join this OP, OQ and OR. That is the extra construction needed. So let us join OP, OQ, OR. OP, OQ, OR. Here you know that OQ is perpendicular to PQ and OR is perpendicular to PR according to the previous theorem. According to the theorem 10.1, angle PQO or OQP and ORP. Angle OQP and ORP are right angles. So you write that one. Angle OQP and angle ORP are right angles. Reason, previous theorem, that is theorem 10.1. What is the statement of that theorem? Just now we proved that theorem. Tangent at any point on a circle is perpendicular to the radius through the point of contact. Here R is a point of contact and Q is a point of contact. So the radius drawn through the point of contact is perpendicular to the tangents. Therefore here, according to the theorem 10.1, OQP and ORP are right angles. Now you take the triangle. Take triangle OQP and triangle ORP and prove that they are congruent triangle. How will you prove that two triangles are congruent? That is, according to any one of the congruence rule, we have to prove that the two triangles are congruent. If you prove triangle OQP is congruent to triangle ORP, then naturally you will get PQ is equals to PR. How will you prove that these two triangles are congruent? In these two triangles, you know that already proved these two are right angles, and OP, hypotenuse OP equals hypotenuse OP, that is the common side, and OQ is equals to OR, they are the radii of same circle. Radii of same circles are always equal. Radii of same circle are always equal. Therefore, according to RHS congruence rule, you can prove that the two triangles are congruent. Right? In triangle OQP, so write in the right angle triangle only, because they are right angle triangle. In the right angle triangle, OQP and right angle triangle ORP, and radii OQ equals radii OR. So write first, you write OQ equals OR. OQ equals OR. Reason, radii of the same circle. Radii of the same circle. Right, hypotenuse OP equals hypotenuse OP, you can write, or otherwise you can leave the word hypotenuse, directly you write OP equals OP common side. OP equals OP common. So you write common side. Therefore you can write triangle OQP is congruent to triangle ORP. According to which congruence rule? RHS congruence rule. So write RHS. Then you can say that according to CPCT, PQ is equals to PR. Right? CPCT. Corresponding parts of congruent triangles. So I got the result here, PQ equals PR.